So the operational data centers, they are in charge of collecting data from core stations, which they're in charge of. Data is then basically transmitted to some regional data centers, and then from regional data centers to global data centers. But it's important that these global data centers, okay, the global data centers, they archive measurement data from the core network. So the same thing what you are doing, they're also doing, but on the global scale. And since this is a budget organization, everything is for free. They don't need to make any money. So you are even able to download the Rhinex files from the network. So not only the Rhinex files, but you can also have access to other products which they generate. And the products and applications which we are mostly interested in are these GPS precise ephemeris file, the GLONASS precise ephemeris file, the Earth rotation parameters. So this is once again important when we compute basically ITRF or some kind of terrestrial coordinate system realization. Then coordinates and velocities of the tracking stations. So not only the Rhinex files. Information about the clock on the satellites. So basically, they provide corrections for the atomic clocks for all the GNSS systems, well, not all, GPS and GLONASS at the moment. Then they provide something called zenith tropospheric path delay estimate. So this is used for basically estimation of ionospheric and tropospheric models, and tropospheric models. And then they also have this global ionospheric map. So the IONEX file, which you have already seen, this is also their product. So thanks to the network of IGS stations, they also can generate this kind of global ionospheric model. And as I said, since all these products are using some kind of or are some kind of result of some scientific activities, then they also closely cooperate with this International Earth Rotation Service, IERS, in definition of basically the reference frame. So these two organizations, they work closely together to provide this, first of all, the realizations of coordinate systems, and also provide this precise ephemeris, precise file product. So here you can see about precise ephemeris, what is the accuracy. So we said that the broadcast ephemeris, the accuracy is about 100 centimeters, and the satellite clock are modeled more or less with this 5 nanoseconds accuracy. And as part of this precise ephemeris process, so there are different, I would say, quality of precise ephemeris files. So those that we use in the Spider are called ultra rapid ephemeris. So you can see the accuracy is about 5 centimeters, and clock information about 3 nanoseconds. So this is for the predicted half, and then we have this so-called observed half. So basically, when they publish this ultra precise ephemeris, 50% of the files are predictions, and 50% of the files are real observations, real computations. So here you can see that the orbits of the satellite are slightly more accurate. It's 3 centimeters. Same applies for the estimation of the clock corrections. Then they have so-called rapid ephemeris, and then they have final ephemeris. And then with the final ephemeris, these are basically released only, let's say, 12 to 18 days after observations. And this is the file which we used in our computation of your coordinates. So basically, after we collected enough data from your core stations, we had to wait additional more or less 2 weeks until these final precise ephemeris are released. But then what we have the positions of satellite with the accuracy of 2.5 centimeter. So this is a significant improvements over this 100, which are transmitted by the satellite. We have also accuracy of clocks on the satellites. You can see that this is a 75 picoseconds. So I don't even know how many zeros it is, but compared to 5 nanoseconds, so it's several hundreds of times more accurate, I would say. So, and this is one of the secrets why when we do this kind of computation with some kind of analytical software like Bernice, this is why the results are more accurate than if you use just kind of standard post-processing software, office software, which is used by standard well, surveying companies, for example. So this is very important when we do this kind of computation of coordinates of core stations. So we use this precise ephemeris files from IGS. We also use the precise clock information. And so the same for GLONASS. Once again, the accuracy, the final accuracy of GLONASS satellite is in this 3 centimeter level. So, and it's necessary to say that it's not only us who is doing this, but also the IERS, International Earth Rotation Service, when they release a new realization of the terrestrial reference system, they also use all these products. So more or less, we are using the same approach as IERS when we compute coordinates of core station. What is important that these products, these precise products, are always related to the current epoch of ITRS realization, which means to the current ITRF realization and also to the epoch of measurement. So when these data were basically measured, or actually when they were computed. So, and now we are coming to the second coordinate system, which I mentioned at the beginning, and this is this terrestrial reference system. So terrestrial reference systems, they are used for positions of the receivers on the ground or on Earth, or the position of users. And these XYZ coordinates of the receiver are then expressed in these celestial or these conventional terrestrial reference systems. The conventional terrestrial reference systems, sometimes they're also called Earth-centered and Earth-fixed. So compared to the Earth-centered inertial, which was this celestial system, because these systems rotate together with the Earth. So the one before, it was basically the Earth rotation was removed. That's why it was called inertial system. This one is fixed to the Earth and it rotates together with the Earth. So once again, the theoretical definition, the origin of the coordinate system is once again the Earth center of mass or geocenter. The Z coordinate axis goes to this conventional terrestrial pole, and the principal axis is basically the intersection of the equator and the mean Greenwich meridian. So once again, if you have a look at these graphics, so this is the geocenter, this is the origin of the coordinate system. It's Cartesian, right hand rotated, plus x axis goes to this intersection of the mean Greenwich meridian and the equator, plus z-axis goes to this conventional terrestrial pole, and we have the y-axis, which complements the Cartesian system. And as I said, this system rotates together with the Earth, and is basically used for basically expressing positions of objects on Earth. Now the problem with Earth is that, as I have mentioned, that Earth is not actually static, and it is broken up into several crusts that we call tectonic plates. So these tectonic plates are in constant movement. Some of them move against each other, some of them move along each other. So you have these basically areas of interaction of the tectonic plates. So these are the areas where you have basically earthquakes, where you have volcano activities. What is important for us is that the control points which are located on these tectonic plates, they move constantly. And here, this is basically an estimation of movements of tectonic plates. So these blue lines are actually boundaries of the major tectonic plates. So we have up to 8 or 9 major tectonic plates, and then we have a lot of small tectonic plates. So, and the good thing is that we are able to actually monitor these movements. Now, when we have this IGS network of core stations, obviously, they not only collect data, that they basically generate something which is called daily solutions for the whole network, which means for all stations around the world. And based on some kind of time, we call them time series of coordinates. So based on the changes of locations of these core stations, that we are able, or they are able to actually map the movements of tectonic plates. And this is basically the map, which is based on the latest ITRF. No, this is not based on ITRF 2014. This is some kind of old plate tectonics map, where it basically shows you more or less how quickly or how the tectonic plates move per year. So this represents 5 centimeter per year. So obviously, the more stations you have, the more IGS station you have, the better you can basically estimate the movement of the tectonic plate. So you can see that Australia, for example, is moving more or less 6 or 7 centimeters per year on the global scale. So this is quite a lot. The same for New Zealand. So these are the areas of I would say fastest moving tectonic plates. So Africa is moving not so much, but still it's about 2.5 centimeters per year. So just keep that in mind, because this is something that also needs to be taken into consideration when we talk about the coordinate systems in GNSS. So the first coordinate system, this terrestrial coordinate system, is called, yes. Yes.
All those in the names in four letters are those IGS stations.
Mm-hmm. Okay. These are IGS stations, but this is from 2007. I have the latest model from 2014. This is just to give you an idea. So the first terrestrial reference system, which was defined, is this WGS84. So this is we say this is the native system for originally for GPS only, but it is basically used as a general term for all coordinate systems used in GNSS technology. So as I said, since GPS was the first global navigation system, then this somehow became a standard. WZ84 became a standard for any kind of GNSS positioning. So it was defined by this Department of Defense. And the thing is that it only provides coordinates of points or stations. Nowadays, it is very close. So it has several realizations that it try to basically estimate this theoretical definition by the monitoring station of GPS system. So GPS, if you remember, consists of the control center, which is somewhere in Colorado Springs, and then they have these monitoring stations distributed in this area. So more or less, they have quite a good coverage. Obviously, not as good as IGS, but they have 16 tracking stations or monitoring stations, which constantly track the GPS satellites, and based on the observations, they are able to define this, or not to define, to realize this WGS84. And there have been several realizations. So the first one was very inaccurate. It was only about 1 meter. So this was initially in the 90s. And we have these new realizations, which are quite close already to this ITRS or ITRF 2008. So also the WGS84 basically over the time was getting more and more accurate. The only problem is that actually the WGS84 coordinates, the realization are basically just these monitoring stations. you do not find any control point with real WGS84 coordinates. This is a common misunderstanding when we talk about GNSS. People are talking about WGS84, but in fact, they are not talking about WGS84. They are talking about something else. But this is kind of a general term that got so much into practice that everybody refers to WGS84. But as I said, the realization, so the points with WGS84 coordinates are only the monitoring stations of GPS system and the satellites. So the GPS satellites, when they broadcast actually ephemeris, then they broadcast positions in this WGS84 coordinates. So normally, if you use your phone, if you somehow get a position, then this is WGS84 position. But this is not actually what we really want in our solution, because this is simply not accurate enough, and therefore we are using a different approach. As I said, this term WGS84 is what coordinate is commonly used for any kind of coordinates derived from GNSS measurement. That's why we will see everywhere WGS84, and but in fact it is not really correct, because what we are actually using is this ITRS. One thing about WGS84, the coordinates are only expressed as XYZ. We have no information about epoch, we have no information about velocity. So this is a general problem of WGS84. And so as I said, we are using a different approach, and we are using this so-called ITRS, or this International Terrestrial Reference System. So once again, this is some kind of global system for estimating positions and also displacement. So this is important. The ITRS coordinates, they always give you XYZ coordinates, but they also give you velocities. So they also give you how much the X coordinates will change over the year. So this is the main difference and a main advantage of ITRS realizations. So this is this time evolution of orientations and the coordinates. And in order to do that, to be able to actually estimate these velocities, there is something called known net rotation. This is some kind of additional condition which is used in the realization of ITRS. And basically, this known net rotation somehow tries to deal with the problem of the global tectonics. Because as I said, all tectonic plates move. So you don't find a static point on Earth. Everything is in motion. So basically, what this NNR condition, what it does, it just takes velocities of all tectonic plates on Earth and tries to minimize it. So this is the main difference between WGS84 and ITRS, that ITRS is somehow dealing with this tectonic plate motions, and using this known net rotation condition, it generates some kind of global, which minimizes these velocities of tectonic plates. It creates realization, or it is used for the realization of ITRS. And the realization is called, as I said already before, ITRF, or International Terrestrial Reference Frames. And these realizations are defined, basically, this is a set of positions at a given epoch, this is important, and also velocities of set of geodetic sites. So this is what we call a dynamic datum. So except for the coordinates, it will also get velocities, and it will get a reference time for which these velocities are computed. And the realizations of ITRS, they do not only use GNSS, but they use also other space techniques. So for example, very long baselines, interferometry, this is one of the spatial techniques. They are monitoring or they are measuring these extraterrestrial objects. Then the satellite laser ranging and the lunar laser ranging. So these are some methods that are using reflection, or they are measuring the positions of satellites or the moon, for example, this LLR. So we have some reflectors on the moon. DORIS was a predecessor of GNSS. So all these space techniques are used in combination because each of them has some kind of internal errors or internal, I would say, systematic biases. So in order basically randomize the systematic errors of these techniques, we use all of them, or not we, the International Error Detection Service together with IGS. And basically the solution which they get is more or less somehow as accurate as possible for the given time. And over the time, there have been several ITRS realizations. So we have this, the first one was called ITRF 88. And then every year, basically, they were doing new realizations, new computations. The difference between realizations were in the techniques used, in the number of core stations which are taken into realizations, and also the algorithmization was basically developing, changing. So this is why at the beginning there have been really a lot of realizations. Basically every year there was a new realization, new computation of the ITRS. In the last years, I would say specifically from ITRF 2005 or ITRF 2008, the differences in realizations are very, very small. So it looks like that more or less we have reached some sort of limit, and this is why the latest realizations are quite separated by year. So since 2005, basically we only had the third realization. So there's ITRF 2005, then ITRF 2008, ITRF 2014, and now we will have ITRF 2020. So these are the realizations of this theoretical system. And as I said, the realization of this ITRF, for example, are the positions of IGS stations, and so the positions are in this XYZ coordinate system, and you have also velocities of all these stations. So typically we have a station in Paris. These are the coordinates. You can see the velocity per year. It's 1.3 centimeter in X coordinate, 1.7 in Y, and 1 in Z. So over the year, the station will move on the global scale by approximately 2.5 centimeters. So, as I said, these realizations are always fixed to some epoch. So you can see that this ITRF realization, ITRF 2014 realization was fixed to this reference epoch 2010.0. So which means that these values are valid for I would say 0 of January 2014. So this is how this should be taken into consideration. Now, if you want to compute positions of this point at current date, at today, then you need to take into consideration these velocities. So obviously, if the position of this station in Paris changes roughly 2.5 centimeters per year, so from 2010, the station has moved roughly by 25 centimeters. So these positions for today are completely somewhere else. And here you can see, basically, it's not very nice, but these are not deviation. Yes, these are just change of position. Your cross stations are moving globally, you know. But we'll come to this. Yes, sorry. No, it was not computed in 2020. It was computed later.
No, from the ITRF of 2014.
Yes.
And then the epoch
It's 20 to 10. Yes.
2010.
Yes. Yes.
Now we gave you epoch of it was 2018 to 2049. How did you compute it? It was in June. When this is
This is the portion of the year. It's a so if you sometimes this epoch. So if you say, where is this? Well, this is a calculator, but it doesn't want to show. Okay. So if you say 0.49, it represents more or less 49. This is the number of days during the per year. So this represents 178th day of the year. Now I will now start another calculator. At least I didn't do it. My colleague did it, so I hope he did it right. Okay, where is this other calculator? Okay, we just have to remember 178.85. I have some problem with my computer. It's somehow frozen. Okay, 178.85. Okay, I will use my phone to do it. So if we start with January. So January has 31 days, 31 plus February 28 plus 31 March plus April 30 plus May 31. We are at 151 minus 178.85 minus 178.85. 27th of June. Well, if we go, it's 28th. What? So he said 29. So this means that this is the we go back. I will make this plus 178.25. So we counted 151 days from 1st of January until the end of May, and 151. So before we calculated that this 0.49 represents 178 days. So 178.85 minus 151. This was the number of days from the beginning of the year until. So this represents 27.85 day in June. So 28th of June, more or less. And what did he say? It was 29. Yeah, I think he wrote it was 29th of June, not 28th of June. So maybe that year was maybe in February we had 29 days. Yeah, but this is how it is translated into a date, you see. So yeah. So and so since we have this realization ITRF 2014, so we have these coordinates expressed in 2010, and we have velocities, then we can easily actually move those coordinates to any epoch. So this is why we can very easily move to the epoch 2018.49, which is yours, using these velocities. Or we can even easily move to the current epoch when we made our computation. So we made the computation for 2022, I don't remember, October or something. So once again, just applying these velocities, we can simply shift along this ITRF 2014 realization easily between different epochs. So this is why we were able basically to shift our computation, which was made for 2022 to 2018. We just applied these velocities of IGS stations which we use. So this is, I'm coming to the next step. Basically, so these velocities you can see here. Where is Africa? Africa is here. So actually, it looks like you are now close to 3 centimeters per year, based on this, I would say. So Zimbabwe, you have an IGS station in Zimbabwe? There is something here. I see this. I see a vector here, which more or less looks like it is, or maybe in Zambia there is some. Okay, so this is Zambia. Because each of these vectors, this represents a GNSS receiver. So this is how they monitor the. So these are, as I said, these are the current realization of tectonic plate model based on ITRF 2014. Yeah. Yeah, the main problem, I don't know about your monumentation. The main problem here with zinc stations is that they would not accept the monuments. The monuments are not stable enough for them. And the second problem is that the monument should be on Earth, in Earth, not on the building.
Okay.
So because they don't want to monitor the shift of the building, for example, because sometimes the buildings, they can vibrate. I don't know. Although I'm not so convinced that this should be a major problem, but they really want to have these concrete monuments embedded into earth and preferably embedded into a bedrock somewhere, which means that you really need to dig quite a big hole for this monument, so typically 4 meters deep and ideally attached to the bedrock somewhere under the surface. So this is the main problem for most of our stations because this type of monumentation it costs a lot of money. So this is why for RTK network or for what you are doing here, these monuments that we do, this kind of pipes attached to buildings, enough. But for IGS and IERS, that's not the preferred way. So, and then obviously they would like to have choke ring antennas everywhere, not this ground plane antennas. So this would be another problem also for your sites because you are using these trimble geodetic antennas. These are not choke ring antennas. So the choke ring are the special design of these concentric rings, and yes. So and of course stable connectivity. This was the major problem at the beginning, so it was not so easy to deliver the data to the data centers. Nowadays, small communication is not a problem because they don't care about streaming. They more or less just want to get RINEX files once per day. That's enough for them. But the problem is the monumentation, mostly, I would say. So this is more or less the ITRF 2014, the current realization, and so we use the IGS network for different purposes. So mostly this type of coordinate system is used for establishing national reference frames. So obviously, okay, also for monitoring the Earth dynamics, as you have seen, and basically for monitoring of variation of parameters for the celestial systems. Right. So, but what is interesting for you is this first use case that the IGS network can be used basically for establishing so-called national reference frames. So ITRF, it's a global reference frame, but it's very impractical because if you have surveyors, they cannot always transform the coordinates to the current epoch. That would be too complex. So normally, when you establish these national reference frames, you have two options. Historically, the control points was the first, basically, and was the first way how, or the first realization of these national reference frames. So, set of control points has been basically reobserved with the reference stations or with the GNSS receivers, and the IGS network. So these are the IGS sites were used for connecting these control points basically to the global network. So some kind of baselines were computed, something like this. And then these control points were sometimes called zero-order control points. But historically, all these control points, they were measured by some terrestrial methods, some kind of altimeters, well, not altimeters, the range, how is it called, total stations. And so these control points typically historically they had some coordinates in some kind of local coordinate system. With GNSS technology, these points were reobserved and connected to IGS network. And then such a realization of the national reference frame was basically connected to this IGS network or to this ITRF at some specific epoch. So this is sometimes called zero order control points. Not all the control points were obviously reobserved, only some set of control points. And these are called zero order control points. So what was important? Some kind of geometry of control points. You should select control points covering the whole country typically, so that you get the best possible coverage. Since you were using long baselines because the IGS stations, especially in Africa, are not so dense, so you can expect long baselines, which means that long observation times were always recommended, preferably several days of data. For example, here we used 14 days of data for the computation of core stations. This could be another reason for the difference that we see, because we use 14 days of data. I don't know how many days of data you use in, or the company used in the computation of your core stations. So yes, yes. So that would be in the report. This is why I was so much interested in having a look into this report. So we always use at least 7 days of data, but preferably 2 weeks of data to really eliminate any kind of blunders, any kind of problems with data completeness, etc., etc. What is also important is to use high quality instrumentation. So for this kind of project, you should never use some kind of receivers from the 90s, for example. You should really use state-of-the-art, latest receivers. And for the data processing, we always recommend to use some kind of scientific processing software because of these long baselines. Because if you use just some kind of standard office software, then the accuracy of baselines would be lower. And then try to model all possible aspects, such as ephemeris, use precise ephemeris, precise satellite clock, use phase center offset, phase center variations for the antenna calibrations, etc., etc. And then, obviously, when you do all that, the coordinates will refer to specific epoch and a specific realization. Let's say ITRF 2093 or ITRF 2014, epoch 2018.49. So, although your coordinates will not have velocities, based on the IGS stations which were used for the computation here, so the IGS stations, they have velocities here. So you can actually estimate the velocities for your whole network, and if necessary, based on the epoch here, you can very easily compute actually the current coordinates, or you can shift along the ITRF 2014 in this case, backwards, forwards, based on the velocities of IGS stations. Yeah, so what is important, obviously, that the accuracy will somehow degrade with time, and it is always recommended to recompute the networks after some years, just to see if you have some kind of local deformations, because this is also something of importance, or something you should know, that except for this global tectonic plate movement, you can have some local deformation, local dynamics. Then obviously also should monitor this. So this is why it is always recommended to reobserve the control points after some years. This was some kind of old approach when the coarse networks were not really in operation. So the current approach is basically replace the control points with core stations, at least some of them, and then basically the approach is the same. But this is significantly simpler because the data from core stations, you can get them basically for every day. So the core stations are constantly recording or collecting data, which means that you can basically compute your network connected to IGS stations on daily basis. So the thing is the same, that if you compute your network, then it is always linked to some kind of realization and some kind of epoch. And but thanks to the fact that your reference stations are continuously operating, so the core stations, then you can basically do this kind of computation even every day. So you can actually monitor your network on daily solutions and basically compute either the new coordinates every day or just after some time update your coordinates. This is mainly interesting for the network processing, which currently you don't have, but so from what I have heard, that you are basically also the your organization, you are planning to basically purchase new core stations next year, or I don't know, or you have already purchased 5 and you are planning. You already have 5, and then another 5 will probably come in the next future, or I don't know, or 10, or I don't know. Right. So I think sooner or later you will implement basically something that is called the network processing. So the network processing, uh, I think you are using more or less the same approach. Is that basically the solution which you deliver to your end users will not be based on single core stations, but actually will use several core stations for one RTK stream. So this is what is called the network RTK. And in that case, since at least in our software we use precise file products which are related to the current realization and the current epoch, then in order to have all in the same realization and the same epoch, you will need to compute a second set of coordinates, at least internally in your software, which will be consistent with the coordinates of precise ephemeris, which is always ITRF, the latest ITRF realization and the latest epoch. So this is why, for example, in our software, we always use these precise ephemeris, which are expressed in this ITRF current epoch and current realization. And this is why we have basically 2 sets of coordinates in our software for each core station. One is this legal coordinates used for production tasks, and a second set of coordinates which is used for estimation of these network parameters, tropospheric, ionospheric delays, and why it is necessary to do. So you can imagine that this is the station, the same station expressed in coordinates, let's say in this ITRF 93 epoch 1995.1. And this is the position of the ITRF of the same station in ITRF 2014 at epoch 2018.3, for example. So over these 20 years, the coordinates of the station has moved by 100 centimeters or 1 meter, in fact. So this is computed for this 3 centimeter per year tectonic plate movement. So this 100 centimeter difference is basically a systematic error which affects the satellite measurement. So the satellite will actually measure this distance, but the system will try to stretch this measurement to fit the coordinates of the same station, but old coordinates, which are in this ITRF 93, epoch 1995-1. So this is why if you use this kind of old coordinates in your network, they will simply not fit with the measurements from satellites. So this is why your network solution will not be solved, and you have to move it to the current epoch in the latest realization. So this is what is requirement. What would be a requirement for the future once you decide to adopt this network RTK approach. So this is the explanation why in our software you will see 2 sets of coordinates. So the second one is just for this internal processing, and this should always be in the latest realization and the latest epoch. So to sum up, these are the basically parameters defined by the International Earth Rotation Service to transform between 2 different realizations. So obviously, so far we're only talking about the ITRF 2014 because your system is in ITRF 2014. Our system is in ITRF 2014. But you can imagine that you have coordinates in different realization. So then International Earth Rotation Service, they also define so-called transformation parameters. So you can actually go from ITRF 2014 to any other previous epochs via so-called Helmer transformation. And this transformation includes basically 3 shifts, 3 rotations, and scale factor. And this can be expressed either as 7 or 14 parameter transformation model. So if you want to go to coordinates, let's say in different realizations, you start with the current realization plus 3 shifts in space, then 3 rotations plus scale factor, and then will give you the coordinates in this new other realization. So this is also something that we normally use, but thanks to the fact that we didn't need to, because we were in the same realization, then we didn't have to use transformation parameters for the coordinates computation of core stations, but we are going to use this transformation, similar transformation, when we will try to basically go to your Gauss-Kruger coordinates. So then we are going to use this type of transformation here. So this is more or less what I wanted to show you related to the coordinate systems. Yes. Seven means only 3 shifts, 3 rotations, and 1 scale factor. 14 parameters means the time factor. That if you make 3 shifts, then you also need to make some velocity estimation. So basically, when you do this, I'll go here. You see that this transformation, actually here are the 7 parameters. Shifts in x, y, z, then you have scale, and then you have rotation x, y, z. These are these first line, for example, to go from ITRF 2008 to ITRF 2005. And then you have basically the velocities or the changes of XYZ shifts, scale, and rotations over the time. So this would be the 14 parameters if you take this into consideration as well. Because you need to understand or need to take into consideration that this ITRF has a different reference epoch. The reference epoch for ITRF 2005 is epoch 2000. And reference epoch for ITRF 2008 was 2005. So we have different epoch. So this difference in epochs, 2005 versus 2000, has to be basically managed by these derivations or these changes of transformation parameters. So this is per year, you know. So this 0.3 millimeters per year. So if you go from 2000 to epoch 2005, it is 5 years. So here then we'll have 1.5 millimeter in this translation component, in this x coordinate. So this is why if you have the same epoch here, then you don't need to use this 14 parameters, only 7 parameter transformation. But if you have different reference epoch, such as for ITRF 2008, the epoch was 2005, so here, then you need to take into consideration this parameter changes, and that's why you need to use this 14 parameter transformation. So this is basically a theory, and now we still have 10 minutes. I'm going to show you the report that we did for your Zinxa network. So based on what I just explained, then not sure why my PC is very slow this morning. So once again, we made a computation of we call it Zinxa course net. So your network, and basically this is when the report was published. This is some kind of introduction. So here in this report, we talk about the reference frame. So once again, we mention all these organizations like IERS, ITRF, etc., etc. So basically, the theory you have already seen. So here we have some summary. Then information about the parameters which we use. So for example, phase center offsets and phase center variation. So this is what we used. We use also calibrations for the stations from IGS network, precise ephemeris, precise pole orientation, and then we have the data set. So you can see we use 14 days of data, including all stations from Zingsa, including your 5 stations. So the data set was quite okay. We are missing some files from Gveru the last 3 days, but this is not critical. So here you can see total number of data sets used, so 14 except for Gveru, where we use only 11. Then this is the list of IGS stations. So we use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 IGS stations. So here's the list. These are the receivers and antennas which are used at IGS stations. And then this is the situation. So more or less, here you can see, yes, ask my colleague to give me a better PDF because. So here are the cores. These are the Zingsa station together with the DSG stations, and the red squares are the IGS stations. So you can see the distribution of IGS stations. Ideally, you should have IGS stations all around your network. So this is what we managed to do, including this side. And this is basically these are the core stations which we took into computation. Now there is some description of how the processing was configured, what kind of data we used, and processing strategy. So we talked about ambiguities yesterday. So ambiguity resolution is always the key factor in every computation. So you see the parameters of post-processing and blah, 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 something you can read that. Now we have the results. So results, first of all, we have the repeatability. So the repeatability tells you something about the internal, I would say, how to say, dispersion of residuals for each individual station. So take into consideration that we use 14 daily data sets, which means 14 baselines based on 1 day computation, and these are basically for 14 days. These are the repeatability. So the differences between daily solution and the final solution. So you can see this repeatability is very, I would say the values are very low, which means good repeatability. So this is in millimeters. So more or less, and this is in not in XYZ Cartesian, but this is in easting, northing, and basically height component. So easting, northing typically always gives you better results because you have satellites basically all around. But height basically is always worse because you have satellites only above the receiver, so not below. So that's the explanation why this kind of height component is always slightly worse. So we can see Gokwe 8 millimeters. This is probably the worst side when it comes to the height. This 9 millimeters. Yeah, but I know why. Because we are going to talk about quality of data, and I have seen at Chimanimani you have a lot of obstructions. You have also some tower there. I haven't been there. I haven't seen the pictures, but I could see in the data some let's say disturbances. So this would be the reason why the repeatability is not as good. But for example, let's have a look at Zingsa. Yeah, this is very good. Very good values because here the situation is very good. You have basically no obstruction. So based on this, you can already understand which sites have I would say better observation conditions than the others. because this repeatability gives you a good information about the sighting, for example. So
you have optimal like
this is more or less normal. Not this is not normal, but when we talk about 2 millimeters, 2.5, this is very good. This is very good, and about 5 millimeters, I would say it's. So here, everywhere where we have something more than 5-6 millimeters, this might be some issue somewhere. But we will see. We can match this, or we can try to match this data with, or this repeatability values with the quality assessment of your core stations that we will do tomorrow. Hopefully, we can get in. So because then we will see, then we will be able to say why we have these problems at some sites. This obviously also depends on the receiver and antenna which you use. But here you can see I don't see any difference between DSG sites and your sites, because the Net R9 is a very good receiver. So also maybe where do you have this choke ring antenna? It's Chimani Mani. Okay, so it didn't help very much. Yes, as this antenna can give slightly better results because of its design, but I think at Chimani Mani you have a different problem. So then, if we combine the solutions, there is solution. Then you can get. We got this list of coordinates. The epoch, reference epoch, is 10th of December 2022. This is basically the middle of these 2 weeks, and so these are the coordinates computed for the epoch of observation. But this is not what we call a reference epoch. So reference epoch is this one. Actually, it's good. It's 2806. So June. So this is basically, since we want to combine your network together with the DSG network, then we need to move this basically stations to the common ITRF, I would say, realization and epoch. And so then this is called a reference epoch. So reference epoch is different from epoch of observation. Reference epoch is this one. So because this was defined by basically the 5 stations from DSG. And then we get coordinates for this epoch 2018.49 or 28th of June. It's the same thing. And so what we did then at the end, we compared these coordinates, the coordinates computed by our solution with the coordinates, which are the reference coordinates for this DSG sites, and we saw some differences. So here, just make it quickly. So these 5 stations, Bulawayo, Gweru, no, Gweru, sorry, Harare. No, yes, Gweru is it's your station as well. Huh? Yeah. Gweru, Harare, Mashwinga, and Mutare. So when we compare our solution, so these coordinates ideally would be the same, but in geodesy and surveying, nothing is ever the same. So we always find some differences, and this is what we see when we compare coordinates which basically were set on the receivers, on their receivers, and coordinates from our computation. So you can see that this is in meters. So we see some differences in, I would say, on centimeter level. So 16, 19, 16, 12, 21 millimeters. So, but this is in this XYZ coordinate system. So it is this Cartesian geocentric coordinate system. So it's very difficult to basically say something about it. It's always better to transform these coordinates into horizontal component and height. So we say, so I made some quick transformation to easting or east-west direction, north-south direction, and height. And here we can see basically that the shift that we see in this east-west direction is more or less very, very, very consistent for all stations. So from -9 millimeters to plus -21. So within 1 centimeter, I would say dispersion, all sides are moved by this 1.5 centimeter, 1.8 in this north-south direction. Here, except for Bulawayo, it's also very consistent from -15 of -8 to -18. So within 1 centimeter, all sides are shifted basically in this north-south direction. And in height, this is the most, basically the highest shift. It's more or less 25 millimeters or up to 30 millimeters below. So yes, that's exactly, this is an exception.